we are going to take a look at direction angles. So first and foremost, when we're talking about direction angles, we are now talking about vectors in terms of trigonometric functions. So in this case, when we're talking about a trigonometric function, in general, we use the unit circle. Unit circle, again, like you can see here, is a circle where your radius is 1, and it's that unit circle that we use in order to measure our known angles. For example, our unit circle like here. So you can see that when you lie along this x-axis, we are at a distance or radius of 1, and then we move up away from the axis in a counterclockwise motion, giving the different angles. So the angles that we know for sure off of a unit circle itself are 30, 45, 60, and thus their counterparts. And so you'll rotate around in that counterclockwise direction. So when we are talking about vectors, we are talking about using the unit circle as part of our helping guide to be able to find the information we need. Now, just like with every vector, we start at the origin, that would be your starting point, and then we're going to expand out and to the edge of the unit circle. And when we do that, we get our terminal coordinate ends up being the cosine of theta, or your angle, and the sine of theta. Now the reason for that is because if we take a look, here we have, say, our triangles. So here, this U right here would be your unit circle, so we know that this is actually going to be a distance of 1. What happens is we've got this triangle here that we can use. So our angle in here, this is the reference angle. And then we have our horizontal motion or movement, which is going to end up being the cosine of your angle I. And then we have the vertical motion, which is going to be the sine of your angle J. Okay, and so that's how we label these 2 points. Well, with that, we can write our component form using our trig idea. So that says we're going to have the cosine of theta and then the sine of theta. So the first term and the second term. And then if we translate that into the linear combination, we get the cosine of I and the sine of J. Okay, and we're going to add those together with linear combinations. Okay. Now that being said, we also have that your components of your vector are going to be functions of the direction angle, which is measured clockwise from your x-axis to the vector. So this is my x-axis down here. This pink line right here would be my vector, say vector u. And then what happens is the angle that it takes to go from my axis up to my vector here is called the direction angle. Okay, so this is very similar to the ideas of reference angles. Okay, so kind of keep that in mind when you're working through some examples or problems. So let's go ahead and do a couple of those examples just so you can see how the math works. So this first one, it says determine the direction angle of the vector to the nearest degree. So we're giving you the vector for -3. So the very first thing that you have to do with that is we have to graph what we know to find our triangle. So 4, -3 is going to put us in that 4th quadrant. So we need to go ahead and draw ourselves our quadrant. My vector is going to come out, say, in this direction. So this would be vector W. And then what we have is we have the horizontal and vertical components. So here we know that my horizontal is going to be 4, my vertical was -3. We are going to spin from the x-axis all the way around in that counterclockwise direction. This is going to be your direction angle, okay, which we would call theta. But then in order to find that, we have this angle right here, which is your reference angle. Okay. Now we are in the fourth quadrant, so if we remember fourth quadrant reference rules, those say that to find your angle, you are going to take 360 degrees and subtract out your reference angle. Okay, so that is what we're going to be doing here. Well, we have to be able to find that. So the first thing that we have to do is use the information that we have. I have an opposite and I have an adjacent. So I have the tangent of my angle of reference is going to be opposite, which is -3, over adjacent, which is 4. So we're going to go ahead and use your graphing calculator to find that angle. So as a reminder, we're going to do the inverse tangent of -3 over 4, and that is going to give us our angle here. So we have -36.8698 blah blah blah. We would round that up. So here what we found is that your angle of reference is going to be -37 degrees. Now that should make a lot of sense because we're in the fourth quadrant, so we would expect that this would be a negative rotation. Now with that, we need to find the direction angle. So here your direction angle again is found by using our reference rules. So my angle is going to be 360 degrees minus that 37 degrees reference. So my direction angle is going to be 323 degrees. Okay. Now notice I didn't use any decimals because my direction said to the nearest degree. Okay, so there's your first example where we were given the component form of a vector. Now, what happens if I want to do the exact same problem, but in this case I give you the linear combination? So here again, we have to do the same thing we just did. Both my I and j terms are positive, so we are going to be here in this first quadrant. So we need to go ahead and draw our quadrant, and we are going to put in our vector. So that means just like before, we've got the horizontal and the vertical components here. So what do we know? Well, we know that my horizontal component, or I, is a 1. And we know my vertical component, which is j, is a 2. We also know that this angle right here is going to be your angle of reference. And with that, we are also looking for your counterclockwise rotation. So here, because we're in the first quadrant, what we need to remember is that my direction angle is going to equal my reference angle. In other words, theta is equal to my theta of reference. And that's just because they both are swinging in the exact same place. So what we need to find here is we need to find that theta value. So again, if we pay attention to what we have adjacent and we have opposite. So we've got the tangent of my angle is equal to opposite 2 over adjacent 1. Again, you could go ahead and use your calculator, but in this case, we are going to find that my angle is 63 degrees. Alright, let's look at another example here. In this problem, we want to find the magnitude and the direction angle for the following vector. So the first thing that I would do is I would start with that magnitude, and then I would fall into finding your direction vector. So here we have the linear component of negative 1i minus 1j. So here my component form then is going to be negative 1, negative 1. So with that we can find the magnitude. So my magnitude is going to be the square root of negative 1 squared plus negative 1 squared. So here we're going to end up getting the square root of 2. And that is your magnitude. Now we have to use this idea, and we need to be able to come up or find our direction angle. Both of my terms are negative, so that tells me that I am down in my third quadrant. So let's go ahead and get our quadrant going. We are going to drop in our vector, which is going to allow us to put in our vertical and our horizontal. Now with that, when we look, both of them are negative 1. So I have negative 1 here. Now, there's a couple things that I need to pay attention to. First, my direction angle is going to be this one in red. This is my theta. However, to get there, I have to be able to recognize or use my angle of reference. Because we are in the third quadrant, what we have to remember there is that your angle of, your angle is going to be 180 plus your angle of reference, and that's going to give you that direction angle. Okay, so let's go ahead and find that reference. So in order to find the reference, I have, again, opposite and adjacent. So this is going to be the tangent for my reference angle is going to be negative 1 over negative 1. Okay? So that's really going to mean that the tangent of my reference is equal to 1. Well, we know that to be 45 degrees. So my angle of reference is going to be 45 degrees. But we could go ahead and, just like before, use your calculator to find that angle. So we know it to be 45 degrees. So again, because we know it to be 45 degrees, my direction angle says that I have to take 180 plus my 45 degrees, and that's going to give me my angle. So in this case here, my direction angle is going to be 225 degrees. Now I found my magnitude and I found my direction angle, and so I have found everything I needed out of that problem. Alright, let's look at one more example idea. So in these two problems, one of the things that you'll notice is that I'm giving you a magnitude and I'm giving you some form of information for your direction angle. And with that, you need to give back to me the component form of your vector as the result. So where you need to start is you need to start with, like always, the picture of what you are looking at. So here my magnitude is 6, but I'm telling you my angle is 30 degrees. So that is going to be your first quadrant. So that's going to be right in here. This is your vector. Again, you can input your horizontal and vertical ideas. Now we know the magnitude is 6. So that is going to be that length or so of your vector here. This is 6. Now the other thing that we know is we know that this part is 30 degrees, and we could call this A and B. Now with that, we need to start putting together our component. And the one thing that we have to remember is we need to remember that the component form when using trig is going to say that V is equal to the cosine of the angle and the sine of the angle. So with that, I can start putting in the information I have. So the first thing that I have is I've got my magnitude here. So that's going to act kind of like your scalar. And then in this case, I'm going to have the cosine of 30 degrees and the sine of 30 degrees. So here, what do I know? I know that this is 6, but I also know what the cosine of 30 degrees is going to be. The cosine of 30 degrees is going to be the square root of 3 over 2, and the sine of 30 is 1/2. Now you can apply your knowledge of scalar multiplication, which says you're going to input the 6. So here I'm going to have 6 over 2, which is going to reduce down to 3 square roots of 3. And then 6 times 1/2 is going to give me 3. Okay, so that is my component form given the information provided. Alright, so let's look at one more giving slightly different information here. So I have that my magnitude is 7, so that is again my length or so of the vector. And then I have that the vector is in the direction of I plus 4j. So both I and j are positive, so again I'm in that first quadrant. So let's go ahead and take a look here. So we're going to input our vector. We know it is 7. We can drop down the vertical and we can drop across that horizontal. And we know that we are in the direction of 1i plus 4j. So that means my horizontal is 1, my vertical is 4. And in this case, what I don't know is the actual angle itself. So here, it's not 7, it's z. Sorry about that. So what we have to do is we have to find your z using your magnitude ideas, because in this case I have given you the horizontal and vertical, and so we need to find its specific diagonal. So this is going to be 1 squared plus 4 squared. So here this is going to be 1 plus 16, which is going to give me the square root of 17. So here what we're doing is we are using the square root of 17. Now I know a lot of students, me included in just this second here, looked at this magnitude and automatically assumed that had to be the difference. Now here's the difference between these two problems. In this first problem here, we're telling you that it is 30 degrees, but I'm not giving you the horizontal or vertical. Instead, I'm just simply giving you the magnitude of a vector. So in this problem, because I don't have a horizontal and a vertical, we can state that my vector here, or the hypotenuse side, was 6. What makes this problem down here different is I did give you the horizontal and the vertical, so we can't just automatically assume that this distance here is 7. You have to calculate it. What that means is it means that this piece right here is going to be your scalar component, okay? Because we want the vector to have a magnitude of 7. And at the current moment, though, it only has a magnitude of 17. Now, the other way that we could look at this is that I told you my angle was 30 degrees. Based on the unit circle, we know that to be the square root of 3 over 2, 1/2, and 1. We would then use this as the scalar to turn it into 6. Okay, I know that's a little bit confusing. Always take that step back and look. When in doubt, solve your triangle to make sure that the magnitude you used here was the magnitude that you should have used in general. Alright, now that I'm going to step down off of that little soapbox here, we need to finish the problem, which says, again, that we need to be able to find our vector in the component form. So v is going to be my magnitude, or my scalar part, times the cosine of the angle and the sine of the angle. So here we are using 7 because that's what we want. We want this to have a magnitude of 7. And then we have to look at the cosine of the angle. So here's my angle, and cosine is always going to be adjacent over hypotenuse. So this is going to be 1 over the square root of 17. The sine is going to be opposite over, so 4 over the square root of 17. Now, after doing that, we have to finish our scalar multiplication. So here we're going to multiply that 7 through, which is going to give us the components 7 over the square root of 17 and 28 over the square root of 17. Okay, and that is your component. Alright, so there are all the different types of examples that you could potentially come across when talking about direction angles. If you have any questions, especially with this last example here, given the use of the magnitude, please let me know. I'd be more than happy to answer that. Otherwise, I do think I have rambled on long enough. I do hope you enjoyed yourself as much as I do, and I really look forward to seeing you again.